This is your lecture that goes with assignment number 14 over topic 8.1. We're going to learn how to multiply and divide rational expressions. So a rational expression is just something that looks like a fraction with variables in it, kind of like number 1 or number 2 that you see here. The first thing we want to do is determine when a rational expression is undefined, which is technically called finding its domain. I want you to think about some rules with fractions because when we say something is undefined, that means it's not possible, it's not real. And that's basically, again, what's happening when you're finding that domain. So you don't want the denominator to ever be a 0. So what we're going to do in the first couple examples here is find out what would make the denominator 0, and that's considered to be the domain of the expression. So the denominator of a rational expression cannot equal 0. This is because division by 0 is undefined. Set the denominator equal to 0 and solve. So we're not paying attention to the numerator at all. You just set the denominator equal to 0. Since this is factored already, we are going to set each factor, x minus 5 equals 0 and the x plus 3 equals 0. We set each factor separately equal to 0 and solve for x. So you would add 5 over to get x by itself on this one, so x would equal a positive 5, and we could subtract 3 over and x would equal a negative 3. So what that means is if you were to plug a 5 into this expression, it would zero it out, or a negative 3, it would zero it out. It's kind of like saying x could not be 5 or negative 3, but we're not going to do anything with that right now. It's just important to understand what would make it undefined. You set those denominators equal to 0 and find the values that would make it a 0 if you plugged it back in. Example 2, notice that in the denominator it's not factored like this one. So really, after you set the denominator equal to 0, we need to factor that and then use those factors to solve. So the first thing we'll do here is look for a GCF when you're factoring. Remember, that's always the first thing you should ask yourself when factoring. There is a GCF. We could pull out 3. So that would leave me with an x squared minus 4. When you divide by 3, that's how we get what's left in that parentheses. The next thing that we could do is factor that x squared minus 4. Remember, that is a difference. There's a minus sign of 2 squares. Both of those are perfect square numbers. So we keep our 3 out, and we set up our 2 parentheses, and we split up our x's, so x and x, and 2 times 2 makes the 4. So we're looking for numbers times itself that make that, right? Because it's a perfect square. And we always use opposite signs, but remember, when that last term's negative, we know we're using opposite signs. Using opposite signs is what zeroes out the middle term, and we don't have a middle term there. Okay, so we set that equal to 0, just like we did here. Now, when we set the factors equal to 0, we're really not setting 3 equal to 0 because 3 does not have a variable. There's nothing to solve there. If 3 had like an x with it, you would. So really the only thing we're setting equal to 0 is x minus 2 equals 0 and the x plus 2 equals 0. So when we're solving, if you add 2 over, that's going to make that x a positive 2, and then when we subtract 2 over, that would make x a negative 2. So x could be 2 or negative 2. If you plugged it in, it would zero out that expression in the denominator. So one last example, find the values of x that make the expression undefined. Again, all we look at is the denominator. It doesn't matter at all what's happening in the numerator. So we set that equal to 0. We ask ourselves if there's a GCF. Remember those questions? No. Is there a pattern? Like, do we have perfect squares on first and last term? No. So we know that we're going to either be doing product sum or slide and divide. Since there's not a number in front of our x squared, we're doing product sum. So since our last term is positive, I know I'm using same signs. And you can list all the products, what times what makes 24. And so I've listed all 4 of them. And using same signs, if I choose the 4 and the 6 pair, a positive 4 and a positive 6 would make a positive 10 middle term when we add them together. So remember, that's what product, listing the products of that number that sum up to make the middle term. So we're using a positive 4 and a positive 6. So we split our x's apart, x and x, and we plug in plus 4 and plus 6. And then we would just set those factors equal to 0. So x plus 4 equals 0, x plus 6 equals 0. So we're subtracting 4, so x would be a negative 4 when you do that. We're subtracting 6, so x would be a negative 6. So x, if you were to plug a negative 4 or a negative 6 into that expression, it would zero it out. So now we're going to move on to writing a rational expression in lowest terms. So what you see here is similar to what we learned in Unit 3. You would just look at that and remember your exponent rules that we learned. We do need to first reduce the coefficient part. If you look at that and you don't see that 9 can go into those two numbers, remember your calculator. Your calculator can reduce it for you, so hit your N over D button, 36 over 27, and it will reduce it to 4 over 3 for you. Or you could have thought 9 goes into 36 4 times and into 27 3 times. And now we're subtracting exponents. So here is the bigger exponent for m, so 5 minus 1 leaves m to the 4th in the top, and for n, we're subtracting 6 minus 3 leaves n to the 3rd in the denominator. But sometimes you're going to have more than one term. So example 4 should be similar, some things that we did back in Unit 3. But in this unit, you might have an expression that you're given. And we can't just cancel expressions the way they are from term to term until they're factored. So we need to always be sure it's in its factored form. Make sure the numerator's factored and make sure the denominator's factored. This example that they've given us right now is already factored. How do I know? There's parentheses in that problem, okay? So then you look for matching factors, or maybe matching parentheses is a way to look at it. And so since I have x plus 4 in both of those, they can cancel out. Now we would reduce this other part just like I did in example 4. So I know 5 goes into 25 5 whole times, and my bigger exponent is in the top, so 3 minus 2 is 1. So this would just be 5x. If you thought of it like this and you said 5 goes into 5 one time and 5 went into 25 5 times, that's okay. But remember, the 1 would then be understood since the variable's all divided up into the top part of that, so we wouldn't want to put it over 1 as our final, most simplified answer. Turning the page, we're going to do a little bit more now. So the next examples are not factored for us. One of the biggest mistakes that students will try to make is to just try to start canceling these to each other as if they were just monomials. But right now, these are binomials, okay? So they're hooked together with that plus sign. The only way that you can do anything different is if you factor something out first. We can't just cancel a term to a term, because right now, I like to refer to these like as people. And I want to say like this is the head and this is the foot. I can't cut off this head just because they have a similar feature, you know. It goes together. It might not be a very good memory device, but that's mine. You cannot cancel term to term when they're hooked together by a plus sign. They are together till the end unless you factor. So looking at the top here, they only have x in common, so look for a GCF. So we could pull out an x. I don't know why we put x equals. We could pull out an x. If you rewrite this and need to so you can show the division of the x that we're pulling out, then go ahead and do that. Pull it to the side. So x goes into x, it zeroes out, so I'm just left with 3. Plus x goes into x, 4. Like this. Okay, here you could pull out a GCF. They have 2x in common, so you could pull that out. So if you do that, you'll divide by 2x. So 2 goes into 6 3 whole times, and 2 goes into 8 4 whole times. And so This was one way that you could have done this one. I can talk to you about another way that this one could have done. Since the 3 plus 4 is the same, we really don't even need to add it, okay? They are matching parentheses, so we can just cancel it out. But then we would want to reduce the front part. Notice that they both have x's in common. If you say that those zero out and nothing's up there, I cannot say my answer is 2 because 2 is in the denominator. Remember, like 1 over 2 means 1/2, and 2 would just mean 2. So you need to be sure to put that understood 1 in its place, and we would just call this one 1/2. You know, $1 million is different than $500,000. So don't forget those understood ones in the top part. Could you have combined like terms in that one and then simplified? Yes. But in the most part in this unit, you're going to not be able to do that generally. So I wanted to go ahead and just do it like the other. Since they're both just x terms, we could have just simplified 3 and 4 make 7x and 6 and 8 make 14x. Okay, then you could have reduced it. But for the most part, like if you look at example 7, we do not have like terms, so we're going to always have to pull out a GCF. Okay, we can't just go, just because I see here, but why can't I reduce my 6 and my 12? Well, because 6x to the 4 is hooked with the minus 24x cubed right now. This is making a polynomial, a specific polynomial. The only way to change it is to factor. And so we look and see 6 and 24 can both be divided by 6. So I'm going to pull out a 6, and they both have at least 6x cubed. So our goal is to factor, see if after you pull out common factors or after you factor, if they have like factors that can cancel. So if you need to, again, you can write 6x to the 4th minus 24x cubed and show that you're dividing by that. So 6 goes into 6 one time, 4 minus 3 is 1, so x to the understood 1. Minus 6 goes into 24 4 times, and the 3's zero out. In the denominator, I noticed 12 and 48 can be divided by 12, and they both have at least x squared. So we want to pull out the 12x squared. And I'll show that division underneath there since there is room. So 12 goes into 12 one time, x cubed over x squared is x. Minus 12 goes into 48 4 times, x squared, 0 out. So once you do that, then you can see, wait, they do have a factor in common. They have x minus 4 in common. So we want to cancel that out. Then we can reduce the front part just like we did earlier. We have 6 and 12. They both can be divided by 6. 6 goes into 6 one time and into 12 2 times. And exponent-wise, my bigger exponent's on top. So 3 minus 2 is 1. So x to the understood 1. But remember, we need to clean that out because that 1 in front of the x is understood. So we do not want to put the 1. So far, the examples, the way they were factoring was by GCF only. How did I know that? Well, I just asked myself, do they have a GCF? And I just started there. A lot of times, two terms will have a GCF if it's set up like that. But if you look at number 8, the polynomial on top does not have a GCF. The polynomial on the bottom is not in descending order. So let's fix that. Make sure it's always in descending order, because to factor, it has to be in descending order, right? So I just rewrote it, a positive x squared, a negative 3x, and a negative 10. So really it's like saying this is over this. I'm going to have to slide and divide this one. Okay, so we're going to have to show our work somewhere. I'm going to do it over here for the factoring. So I'd have to slide my 6 to the back, so I have x squared plus 7x plus 12. Using same signs, since that's a positive 12, I need to make a 7. If I take 3 times 4, that is 12. And if I add those together for product sum at this point, that would make 7. So I'm going to plug in plus 3 and plus 4. If they're both positive, we could make a positive 7. But remember, in slide and divide, we're not done. We were factoring the temporary polynomial that we made after we slid the 6 to the back. So we have to put the 2 underneath both. Well, 2 won't go into either of those. I wrote 3, sorry. 3 and 4. There we go. That makes sense. So 2 will go up front here because it doesn't divide up into the 3, but 2 can go into 4 evenly, so we would simplify x plus 2. So we just need to come over here and write those factors in the top part of a fraction, since I don't probably have room to put the factors of this one underneath that. Okay, so what we did was I just showed my work of the factoring for the slide and divide one. Now I need to factor this one. Since it's a negative 10, I know I'm using opposite signs to make a 3. I know 2 times 5 is 10. If I had a positive 2 and a negative 5, that makes negative 3. So we're going to split our x's apart, x, and plug in plus 2 minus 5. So we have 2 binomials in the top and 2 binomials in the bottom. We need to see if any of those binomials match exactly. We can call this George and this George. We have 2 Georges, so let's cancel our Georges out. But this is Sally and this is Mary, so we can't cancel them out. They're 2 different polynomials. Okay, so we have 2x plus 3 over x minus 5 that we just leave. Again, we can't cancel a term to a term. This is now a polynomial that I'm going to name Sally. And this is a polynomial, Mary. They're 2 different polynomials. If factoring seems like it's going fast for you in this lesson, make sure you pause between. Practice factoring on your own, because this unit that's the basics of everything you're going to do. You have to factor first. There is no other way. Example 9. So again, we look and see, is there GCF? No. Is this a pattern? No. So I like to go through those 2 questions first. This was not a perfect square. I'm just looking at the top right now. And so I know I'm using product sum. Since that is a negative 15, I'm using opposite signs to try to make a negative 2. If I had a positive 3 and a negative 5, that would make the negative 2 middle term. So I split my x's apart, x and x, and plug in plus 3 minus 5. The polynomial in the bottom is a difference of 2 squares. So we can take x times x, that makes x squared, and 3 times itself to make 9. So we set up our parentheses, x and x, and plug in our 3's. 3 times 3 was 9, and remember you're using opposite signs also. It's a negative just like the other, so we have positive and negative. Oh, I wrote plus, but I said negative. There we go. So notice we have an x plus 3 and an x plus 3. They can cancel each other out. So what you're left with is an x minus 5, Joe, and x minus 3, Tina. So I know it's kind of weird. I'm just naming them to make sure you know it represents something specific. Even though they both have a head, x, we can't cut their heads off just because they both have a head. They're a polynomial. It's a binomial. Keep them together. Don't try to cancel them. And I keep really going over that because students do it a lot. Okay, and as we move on, you're going to learn about multiplying rational expressions. So really what we just did is pretty much what you need to always make sure and do. If you have more than one term, make sure you factor the polynomials that you're given first. Then we can start canceling out. If you notice in example 10, this problem, it is just monomials. So we will just reduce or cross-reduce if you want. So you can reduce any top term to any bottom term. The 16 and the 35, 28 and 48, it doesn't matter. It just depends on what you see and the numbers, and that's okay. I noticed 16 and 48, they can both be divided by 16. So 16 goes into 16 one time, and 16 goes into 48 3 times. What if you didn't notice that? It's okay. Just make sure that you pick a pair, reduce them, and just continue to reduce the numbers until they can't reduce anymore. And then I also noticed on the next example, or not next example, sorry, on the 28 and 35, we can divide both of those by 7. So I like to circle them so you know those are the 2 I'm comparing, and I look and think, what can they be divided by? Can they be divided by a common number? And they can. 7 goes into 28 4 times, and 7 goes into 45 or 35 5 times. Again, you may have reduced it, 16 and 48. Maybe you started with 2 or 8. That's okay. You just would have reduced the numbers again until you got maybe a 1 and a 3. I have a 1 and a 5, a 4 and a 3, so nothing can reduce anymore. So I'm going to multiply 1 times 5 is 5, and 4 times 3 is 12. So that's as reduced as the number part can get. I like to rewrite the variable parts again. I don't like to, when it's monomials like this, try to reduce because I get lost. So I'm going to rewrite a squared, b squared, x to the third, y to the fifth. Why did I put the a's and b's before x and y's? Just because it's in alphabetical order. It doesn't really matter. I'm using the same thing. I'm just put it in alphabetical order. That way they're kind of right above each other when we go to reduce. So my 5 and 12 is as reduced as it can get. We are going to reduce our variable part. Bigger a's in the bottom. 3 minus 2 is a to the understood 1. Bigger b is up top. Except for b, 2 minus 1 is the understood 1. X is bigger. So 3 minus 2 is 1, and our 5s are the same, so they zero out. But if you look at example 11, it's going to look differently. It's going to seem like you're doing something a little bit different first. We can't factor monomials, so that's why we just did the cross-reducing and reduced the variables by subtracting. But in example 11, you want to factor because you see that there's more than one term up here. It's separated by a minus sign. Factor this. I can't factor these two things. They will just stay what they are. So let's first factor this one. I notice that 12 can go into both of those terms, and they both have x's and y's. The smallest x they have is x, and the smallest y they have is actually y squared. So we're going to factor out a 12xy squared. And if you need to write this somewhere to show the division step of dividing out that GCF of 12xy squared, then please do that. So 12 goes into 12 one whole time, x squared over x leaves you with x, and the y squareds zero out. Minus 12 goes into 24 two times, our variable parts zero out. Probably should have pulled that in there. We're just going to do that. And that 3z to the fourth can stay the same over there on its top. Down here, this 5z squared stays the same, but we can factor this binomial. So 4 can go into both of those, and they both have x's. The smallest is x squared, and they both have y's, and that is the smallest. So you can show your 4x squared y underneath to show how you're going to reduce that. 4 goes into 4 one time. X cubed over x squared is x, y zero out. Minus 4 goes into 8 two times, and our variable parts are both the same, so it zeroes out. So at this point, we can start canceling. I like to think, really, when it says times, you can kind of think of it one big line. Any top to any bottom can reduce. But this and this are the same, so we can reduce. If you want to rewrite this to clean it up, like a monomial over a monomial, and do what we did here, that's basically what we're doing now. I'm going to show you that 4 and 12 are the two numbers I'm comparing right now to reduce. 4 goes into 4 one time, so I cross it out and put a 1. And 4 goes into 12 three times, so I cross it out and put a 3. Coefficient-wise, I just have 3's on the top and a 5 and a 1 in the bottom, so we can't cancel any top to a bottom right now. So I actually kind of ran out of room, so I'm going to come up here. I apologize for that, but 3 times 3 is 9, and 5 times 1 is 5. I wrote way too big. And then I will rewrite the variable parts like I did before. So I have x, y squared, z to the fourth. So I'm just looking at all the tops. I'm rewriting the letter parts. X squared y and z squared. That way I can remember how to reduce them. So I have 9 over 5, and then we'll reduce the letter part. So 2 minus 1 leaves me with x in the denominator. Y squared over y to the 1 leaves me with y to the understood 1 in the numerator. And for z's, we're subtracting 4 minus 2, so that's z squared. The next example, we have 4 different trinomials that need to be factored. None of them have a GCF. I can just see that right now. None of them have a number in front of x squared, so we can just simply do product sum method. And I will probably factor these quick, so I strongly encourage you, pause the video between each one. Just so that my video is not super long, I'm going to go through the factoring. So 2 times 3 makes 6. I know I'm using opposite signs, so if I had a -2 and a +3, that would make that positive understood 1 that's in front of that x. So those are the pairs that we'll use. So x minus 2 times x plus 3 are the factoring for that first polynomial. Using opposite signs again, since that's a -12, if I take 3 times 4, that makes 12, and if I had a +3 and a -4, that would make the -1 for that middle term. So I'm going to have x plus 3 and an x minus 4 in a parentheses. Times the factoring of these polynomials. So again, negative in front of that last time, so it's opposite signs. I'm trying to make a +1. So 4 times 5 is 20. A -4 and a +5 make a +1. So we have x minus 4 and x plus 5. And lastly, I'm using same signs to make the middle term. If I take 2 times 2, that makes 4. And if they're both negative, that would make the -4 middle term. So x minus 2, x minus 2. So you will have to do like 4 factoring problems in that one problem. Then we can cancel out like factors. X plus 3's cancel, I notice. Just here, I usually work left to right to compare, but x minus 2 and that x minus 2 cancel. You can only cancel 1 to 1. I have an x minus 4 and an x minus 4 that cancel. And then I'm just left with an x plus 5 over an x minus 2. So hopefully you really mastered factoring in the last unit, because that's what you have to do first in all of these. If you don't factor, I can't give you any points for these problems, you know, like on a test when you're showing your work. So make sure that you really practice factoring each one of these. If you ever have questions, refer back to your Unit 3 notes in your factoring. All right, up here, again, we should always look and see if there's a GCF first, especially if you just see 2 terms. And so here I notice they can both be divided by 3, and they both have at least x. They don't both have a y, so I cannot pull a y out. So I'm going to rewrite it right here just to show you the dividing of that GCF. So I just rewrote it since there's not room to show the division. So 6 divided by 3 is 2, x squared over x is x. Minus 3 goes into 3 one time, x is 0 out, and we have a y. Could you put a 1 in front of that? Sure. But you don't have to. So 10ab to the 4th can't factor because it's just a single term. Neither can 15a squared b squared. It's just a single term. But down here, there's 2 terms. They're separated by a minus sign. It's a binomial. So we can pull out an 8 because they both can be divided by 8. They both have an x, the smallest being x, and they both have a y squared, the smallest being y squared over y cubed. So you can show that division of the 8xy squared. So 8 goes into 16 2 times, x squared over x is x, and our y 0 out. Minus 8 goes into 8 one whole time, x is 0 out, and 3 minus 2 is 1. So if you want to put the 1, you can, but remember you don't have to. They are matching, so we can cancel those out. Then we look at our variable parts and decide if we can reduce. So I noticed like 15 and 10 can both be divided by 5, so 5 goes into 10 2 times and into 15 3 times. From there, we can't reduce any top to any bottom, right? 3 can't go into 8 or 2. We can't do any of that. So we're just going to multiply the coefficient parts. 3 times 3 is 9, and 2 times 8 is 16. And then I like to rewrite the variable part, a squared b squared, and I like to do it in alphabetical order, x, and ab to the 4th, xy squared. Then we can reduce the letter part, so we only see a, b, and y, a, b, x, and y once, if you even get to see them all. So 2 minus 1 leaves a in the top, 4 minus 2 leaves b squared in the bottom. X is 0 out, so we're not going to have any x's in that one, and you are going to have a y squared in the bottom. And lastly, on this lesson, you will be learning how to divide rational expressions. Remember your rules with fractions. You really never divide fractions if it was like 1/2 divided by 3/2 or something like that. You always had to flip the fraction to the right and you change it to multiplication. So that's basically what we're doing here today. We're taking this and we're going to flip it and make a new problem. So this is really 22p squared q over 12m n to the third. And you're going to be multiplying now. So since this is these are all one single term, we can cross reduce. And you can look at any number to any number, like 9 and 12 has some like factors. So I'm going to look at those. They can be divided by 3. 3 goes into 9 3 times and into 12 4 times. The 11 and 22, 11 can go into itself once and into 22 twice. Some of you might have wanted to reduce these two numbers first, and that would have been okay. They both could have been divided by 12 maybe. But that's why I say sometimes our eyes are drawn to reduce a little bit differently. So 2 goes into 2 one time and 2 goes into 4 2 times. So be sure you reduce it to its most reduced form. Sometimes you don't just reduce one to one and the other to another and then be done. Sometimes you still can reduce further, like this one did. 3 times 1 is 3 and 1 times 2 is 2. And then we can write, I like to write my letters still, p squared q and m n cubed p q squared. And then we can do that reducing. So 3 over 2 is reduced, and we're just subtracting 3 minus 1 is n squared. 4 minus 3 is n. 2 minus 1 is p, and q's in the bottom. 2 minus 1 is q. Okay. So we're going to be flipping and multiplying, so I'm just going to write it above. So this needs to go up here, and this should be down here. And we're really multiplying, so we've changed spots. So really this polynomial is on top, this polynomial is on bottom, and now we're multiplying. So we just need to factor all 4 of these. So looking at this one, there's not a GCF. And it is a product sum. If I take 1 times 5, I can make 5, and they can add up to be a positive 6 if they're both positive. So w plus 1 and w plus 5. This one has a GCF. I notice it's squared, so I'm going to pull its GCF out here first. They both can be divided by 3. I don't know why I pulled my calculator over, but anyways. So we have y squared minus 9. And that can factor just a little bit more, right? Because it's a y or w squared. So we're going to write those factors here. Our w's apart, that's a difference of 2 squared, 3 and 3. So plus and minus. So the more you factor, the more you'll get good at asking yourself those questions, and you'll be able to see it. Hopefully you've already mastered it from the previous unit. 7 and 21 can be divided by 7, so that would be left. We would be left with w plus 3. And then here we're using same signs to make 10. 5 times 5 is 25. If they're both positive, that would make 10. So split your w's apart, and 5 and 5. Again, please pause if you want to factor them yourself to practice. First thing that I see is there's not any w plus 1, so I know that's going to stay up there. There is a w plus 5 that can cancel, just 1. And there is a 7 that can cancel on the top and the bottom. And there is a w plus 3. Be sure you cancel the ones that are the same. Be careful not to cancel these two, because this was a minus and this was a plus. So this was left over down here. So we have w plus 1 over w minus 3. 2 more examples. This video is getting kind of lengthy, so I'm going to try to do it kind of quickly. Like I said, again, please pause. So we have to flip. This comes up on the top, and this comes up on the bottom. And so you're actually multiplying when you do that. All of these have GCFs. I see just 2 terms, so it's a good indication that you're looking for some GCFs. And we have x in common here, so we're just pulling out an x. And maybe you can squeeze it in underneath there like that. So you have a 3x plus 2. Here they both just have y in common, so you could only pull out a y, so that would be a 2x minus 3. Times, they don't have numbers in common, but they do have y cubes in common, so we can pull out a y cubed. So that would leave you with, I'll write it underneath, that will leave you with 2x minus 3 over x squareds are in common here. It's the smallest x that they have, and they only have x's in common. So we're going to divide by x squareds. That would leave you with a 3x plus 2. So we do have some matching parentheses, 3x plus 2. We do have a 2x minus 3 that's the same. If you would like to, I would still, just by habit, rewrite those variable parts because I get kind of mixed up and I might forget to reduce something. When I subtract my variable parts for the x, it stays in the bottom. 2 minus 1 is 1, and y squared would be in the top. Your last example is going to take some effort in factoring. In fact, I'm going to use a blank piece of paper to just show you all the factoring. The first thing that you have to do in this problem, I'm going to keep it over here to the left, but I'm going to write the work over here, is we do have to flip the fraction to the right. So these first two things stay the same. But we're flipping this because it says divide. So because of the division symbol, we flip it. So my 5x squared plus x minus 4 is in the top, and my 4x squared minus 8x plus 3 is in the bottom. And so be sure you always flip, and then it just looks like the examples that we did before, the division of rational expressions that we learned. None of these have GCFs. They all have a number in front. So all of these are the lovely slide and divide problems. So we need to be sure and slide and divide each one. So I'm going to do that. We're going to say 6 times, and I'm going to leave this here. So when I find the factoring, I'm going to just put them here so you can see it kind of in a good spot. So we have 6 times 2 would make this a x squared minus 7x plus 2. When we factor it, we're using same signs to make a negative 7. If I had a negative 3 and a negative 4, that's same signs, and they would add up to be the negative 7. So x minus 3 and x minus 4. I had to go put my 6 back in, so the divide part of slide and divide. But we can't just pull these up front. We need to reduce them. So that'd be like saying 1 over 2, because 3 can reduce both of those. 3 goes into 3 once and into 6 twice. With these reduced by 2, which would leave you with a 2 over 3. Now we can pull some things up front. So this would be like saying 2x minus 1 times 3x minus 2. So you might need to have paper on the side and do the factoring. Once you find the factoring, it goes up here in the top. So 2x minus 1 times 3x minus 2. Now we'll do the factoring of the denominator. So I'm going to move this over here. So we have x squared plus x minus 6. 3 times 2 is 6. Using opposite signs, I could make an understood 1. 2 times 3 is 6. If I had a negative 2 and a positive 3, that would make 1. So I'm going to split my factors apart, x and x, right? And then we get to plug in minus 2 plus 3. So we factored this temporary polynomial. When we slid the 3 to the back, let's divide. We divide by that same 3. So this one, 3 can't go up into 2, so we just pull it to the front. But here we can reduce, so that'd be like saying x plus 1. So we put that factoring here, 2x minus 2 times x plus 1. And the next one, we have the 5x squared plus x minus 4. If I multiply 5 times 4, I'm going to have to move my paper, but we have x squared plus x minus 5 times 4 was 20. Using opposite signs, if I take 4 times 5, if I had a negative 4 and a positive 5, that would make that understood 1 middle term. So we have x minus 4 and x plus 5 in our parentheses. Now we need to put that 5 back into the problem that we slid to the back. So we divide by 5. So I'm going to pull him up front. So 5x minus 4, but this can reduce to x plus 1. So let's come up here and put those factors there. 5x minus 4 and x plus 1. And then the last one, I'm going to just factor it right here. The 4x squared plus or minus 8 plus 3, we're going to move the 4 to the back. So we have x squared minus 8x plus 12. I just put a line here to separate it from my work there. So we will be factoring, this is a positive 12. If we take 2 times 6, that makes 12, and if they're both negative, that would make them negative 8. So x minus 2 and x minus 6. Now we put our 4 back into the problem, so divide by 4. This is one, again, kind of like this first one, where the factors can reduce. It doesn't divide up into 2, doesn't divide up into 6 evenly, but like we can reduce. Both of those can be divided by 2, so that'd be like saying 1 over 2. And both of those can be divided by 2, so that'd be like saying 3 over 2. So then we could pull some 2's to the front, making that 2x minus 1 and a 2x minus 3. Not forgetting, I didn't go over it here because you should be doing it on your own from the previous unit. Checking yourself, 2x times 2x made my 4x squared. Negative 1 times negative 3 made that positive 3. My inner term came from the multiplication of our inner and outer. It's just that you should know how to do that now, and hopefully you're continuing to practice that. And so I write the factors here because that was the factoring that we did here of this polynomial. Okay? So yeah, we got to do all that factoring. Now we need to go look and see, can any factors cancel out? Sure they can. We have a 2x minus 1 and a 2x minus 1 that cancel. I don't have a 3x minus 2 down here. I don't have a 5x minus 4, but I do have an x plus 1. So sometimes you have more than one parentheses. And if so, you just write them beside each other. Okay, you just write 3x minus 2 times 5x minus 4 over 2x minus 2 times 2x minus 3. You don't have to FOIL, you don't do anything like that, you just leave them as in factored form as parentheses.